and Adam Siddiqui, and we divide the presentation in 3 different parts. The first part I will give you, and for the second part, Adil will come here, and for the last part of the presentation, Siddiqui will do. And the first question is, what is the difference between FEM and mixed finite element method? There are 2 differences. First, for the finite element method, you see that the given differential problem in which we have underlying derivative, they are approximately to lower order rather than their original order. But in the mixed finite element method, the given differential problem, the underlying derivative are approximately to same order as they are given. And the second, in the mixed finite element method, in the finite element method, we use one approximation space. And in the mixed finite element method, we will use more than one approximation space. This is the difference. And third difference, which is not mentioned here, is the procedural difference here. The major steps are the similar. As you look at this flow chart, first we have our differential equation, our problem, then we will make its weak formulation by some method, and then after weak formulation, then we check its existence of the solution by there is a condition which we call the Weisskopper-easy condition, similar to the Lex medium as we do in the finite element method. Then we have a discrete form of this problem, and then we again check the existence of the solution. After we have a linear system, then we may apply the appropriate matrix method to solve that system. This is the flow chart, and I will give you up to the weak formulation, then Adil will come and explain up to discrete form, and finally for the linear system, Siddiqui will come here. So this is our model problem. This is the second order elliptic differential equation with Dirichlet boundary condition. And here omega is a polygonal domain in R2. Polygonal mean triangular, square, rectangular, and so on. So we have a piecewise smooth domain. And then this A should be a smooth with positive, you can say, in the omega and its boundary. And F should be a L2 functional. We have here in this problem. And for the simplicity, what we did, we choose instead of A here, we choose A equal to 1 for some good reason to make this, to understand this process of mixed finite element method. So by taking A equal to 1, our problem becomes like this. Other conditions are similar. Then here we have a difference as compared to the finite element method. In the finite element method, we direct multiply some suitable function here, then integrate over our domain. But here we will first make this one differential equation in 2 different parts by applying this substitution. We apply del P equal U. So this equation converted into what? 2 different differential equation in omega, and the boundary condition is same. Then this is the weak formulation construction. Now we have 2 differential equations, this one and this one. Here we apply the same finite element method construction for the weak form. For this we have this weak formulation, and by applying the Green's formula, and you see there is a boundary, and on the boundary P is equal to 0, so this term will vanish. So we have this weak formulation for this first equation, and here we have a weak formulation for our second equation, this one. Then after this we reach to weak formulation equations, that is find P belongs to W, U belongs to V, and or you can say we have to find this order pair, UP, U belong to V and V belong to W, such that these 2 conditions satisfy for all V belongs to V and for all W belongs to W. Then here we have these integrals, these are the inner products. All are, for this we have this one, then second, third and the fourth one. And here are our approximation spaces. V is simply H1 omega and W is L2 space. Next, here we first check the boundedness for this operator. In general we can show this. This is bounded. Look at here. This is our integral. Then we apply CS inequality, shahbaz. Then this will less than from this is equal to this one. This is the norm, and this is the norm of V. And we know from point K inequality, this is less than this one in general, H1 norm. So this is bounded, and also this is also bounded. FW, similar procedure by applying the shahbaz inequality. Then this is L2 norms. And now this is the crux of our presentation, you can say. We have to find the existence of a unique solution. This is the Boveska and Parisi conditions. If we have, first we prove that to boundedness for the linear functional and for the inner product A, and if we have plus these two conditions, then this is the guarantee that our problem has a unique solution. There exists a unique solution to our problem. And look at here. This is a subspace of V. In general, we prove in V that the previous bounded condition. But here we are applying the subspace of V due to some good reason that this condition will satisfy. So this is sometime called kernel of V. Here we have this term this inner product goes to 0. On this space, we have proved that these two norms are equivalent. And this will then help us in proving the coercivity and in-suit condition of Boveska-Parisi. Equivalent, you can see, if we apply, this is in general less than this one, H1 norm, and H1 norm square is equal to this one. Then this can be written like this, and by this condition, this will equal to 0 because we are doing in Z, not in V. So this will less than this one, so this, which means these two norms are equivalent. And by this help that these two norms are equivalent, we can now prove coercivity of VV in space Z. Z is a subspace of V, original space. This is for the coercivity, we have to prove this is H1 square greater than this inner product. This is equal to this one because these two norms are equivalent. So this is greater than equal to H1 norm square. So this is coercive with here we have a constant alpha not equal to 1. Then the main in-suit condition. We also prove this one in Z space, Z cross W space. We are not proving it in the original V cross W space. So here we use the coercivity of this one, start with this coercivity. So this will be less than this one, then we can write it in two parts. And then we what we did, we apply V equal to W for W. So this will go like this. Then the norms are equivalent, so this will be greater than, yes. But no need. Equivalent norm in general from the point K inequality we also apply this condition. And from this here, we use this condition to write this one minus, this is negative, so this negative is less than the positive. This positive, then so we have this equation, this inequality. So then we divide by this one, both sides. So this will go like this. So this will be less than the supremum if V is not 0. If we have V equal to 0, this will go wrong. So that's why we apply that the vector will not be a 0 vector here. So this is the condition, the fourth and the last condition of Boveska-Parisi, to which guarantee us that our problem has a unique solution. So our problem exists a unique solution. Now I will call my other friend. He will proceed.
So we ask questions set by set or all together?
Okay, if you have the questions, yes.
One thing I like is that you don't have numbers on your slide. So, that's just a remark. Always have numbers, because if anybody wants to go back and, ask, plus you know how much going on. But could you kindly go back? It's not a question, I don't understand that. What does that mean? Could you please keep going? Yeah, what does this mean? V1 now is less than equal to square and V square?
This one?
Yeah.
This is L2 norm. L2 norm square.
Oh, okay.
This is H1 norm. So these two are equivalent on space.
But this is less than equal to that and also greater than equal to.
So if we have a constant, here we are using the constant. Constant is 1. Here we have also 1. So if we have such condition, it means these two norms are equivalent. Any two norms are equivalent by these two inequalities, combined inequality. So
whenever you do not put the 2, that means it is a 2 norm.
Yes.
Oh.
Yes.
Okay, so far Mr. Shahbaz has discussed about the weak formulations and existence and uniqueness of the problem. Here we have 2 weak formulations. Basically, as he discussed, we consider the elliptic problem and then weak formulation, and then using the input condition, he shows that there exists a unique solution. Now the other part is that these solutions can be characterized as a saddle point, which satisfies this relation L of S P less than equal to. This is the basic inequality, which is here representing that the solution U and P satisfying the or characterized as the saddle point conditions. Now we will prove this by using the definition of L of ST, which is given in the equation, and for here S and P belongs to B cross P. By solving this 1 by 2 and S squared plus del S plus F times T, and making U belongs to V as S belongs to V. So here we using just replacing S by U and using the definition, and since U norm is less than equal to 1 U norms, and keep going like this, and we have L of U, L of SP is less than equal to L of UT. So the solution UP can be characterized as a saddle point of the minimization problem, because we can show that, or we can write that this weak formulation problem can be characterized or represented as a minimization problem. This we have done in the this we have done for the 1D problems.
What is this capital U?
This is by mistake.
Yes.
This is small u. This is the composing mistake.
So there are 2 mistakes. And you got to proofread, remember very carefully. Because we are talking informally, and just a guess, it doesn't mean. But one very important point is in life, that when you expose yourself publicly, you cannot do one mistake. Because you are out of business. Someone, if you are presenting, like we have students to companies and things like that, so proofread it very, very carefully, 2-3 times and things like that. I mean, academically, here professors are kind and all this thing, but when you go to the real world, like the companies and things like that, people are not kind, because there they give you money, right? So they can't give money to the wrong people, right? So just, in the future, this is a very good practice that you are getting inside the class and the projects, especially when you go to theses like job market, for example. So suppose if we don't tell you at this time, and you continue doing that, then you will curse your professors. Oh, why didn't they tell us, right? So just a point, it's nothing, taken any wrong way. Yeah.
So as we did in the 1D problem or finite element method, first we have reduced the problem into weak formulation, then we introduced the discrete formulation. For this we have 2 spaces, and there are two weak formulations, so we need 2 spaces. P which is a subset of P, and similarly W is a finite dimensional subspaces. Now we have to find a solution which is discrete one, UH and PH, because in the weak formulation we have U and P, and in the discrete case we have UH and PH, which belongs to the WH, PH belongs to there. we satisfy the, again, we are using the V formulation, which we have already done in the previous slides. Here UH, VH plus PH times del dot UH is equal to 0. This is again the same problem which we shows in the previous slides. Next, for this, again we have to show the condition which we have done in the V formulation. First we have to show that UH and VH less than MV boundedness. We have to show this is bounded, and then we have to show boundary linear functional, next coercivity, and the last one in sub condition for their discrete formulation. Here we can see that the boundedness and bounded linear functional we can see as we have proved in the V formulation, that is the V and infinite dimensional spaces, and VH and V is a subset of V, so this holds automatically in this case, in discrete formulation. So there are two main things we have to show in this problem or in discrete formulation, the coercivity and the in sub condition. So we define two spaces VH is like this phi such that phi belongs to V, where phi's are piecewise quadratic, and WH where WH is piecewise linear functions, where and the triangularization is defined as tau h on the whole domain of omega. So for coercivity we consider VH belongs to V, and here VH are the linear combinations of local basis functions and the unknown Vj. So by writing in inner product form or considering the same V formulation, we are using here and show that this is coercive for alpha not is equal to k. Yes, where k can be constant. And next, in sub conditions for discrete space, it can be similarly observed as we have done in the V formulation cases. It can be followed as it is from the previous slides, similar to these slides. And yes, in this case, I would like to invite Mr. Azim for the matrices. Good evening, everyone. As far as my part is concerned, it is the final and last part, that is the linear formulation or the linear part. It consists of a system of matrices that we have obtained from the V formulation of the three equations. And this is the finite element matrices. In the usual way, we choose basis, like as far as we know that these are the finite discrete spaces, subspaces that we these are belong to like V and W space, but VH and WH are basically the discretized spaces, subspaces of those two. And these are the members of those two, like span, phi, I, matrix and its members. And then we define the finite element matrices as A, which belongs to the real number set, by Aij, which is basically this type of formulation between the 1 and n number of n numbers. And similarly, we define the matrix and its elements by this thing, and the range of is 1 to m and 1 to n separately for Pi and j. Similarly, the elements of V is this is the basically this matrix 0 and minus n load vector we say. So this is basically also a subset of which belongs to the real number pi, and we denote it by this. So now we can now we have a system of equations of matrices here, so that we can solve and get the required solution, which is 0 u and v. There are two solutions unknowns in this equation.
This beta j is a vector
Beta.
over there. Yeah, keep on going this way. You have
This
del
one?
dot, yeah, in the parentheses.
Yeah.
Go further down. Yeah.
This one?
No, same, up there.
Yeah. V is
No,
basically a matrix. V
Okay.
is a matrix
Okay.
which belongs to real number, and its elements are denoted by this.
But what about this
This
beta?
generated by this inner product.
This is
in the
basically
weak form.
an inner product of beta I and gradient of beta j, And these values,
No, but beta j is a vector.
beta j,
It's not a vector, right?
It's
Yeah,
not a
it's-
vector.
yeah,
It's-
Put a dot there. See there?
yeah, it's
So
a scalar.
because it's a gradient, so you are having a vector or scalar, so it
Nice.
cannot be a vector.
And this,
Gradient of a scalar is
But that's why I was confused. They are dot product.
Sorry, it was mistakenly. So now after this we have a system of matrices. A is a matrix, B and its transpose. So we get we have also learned a lot of methods in order to solve the linear system, like in MATLAB, as our professor did. So we can have the solution. But here is the A matrix is symmetric positive SPD matrix. So this is it. Next is these are the references which we have took from this finite element method, and the Gracie and Babushka method was from this book, and also these are the other things which we have. Thanks.
Okay, thank you. Any questions or comments?
What,
Yes.
one question.
Yeah, okay, go ahead.
What are the advantages of this mixed diagram? Because you are using more than one domain space, as you said in your initial introduction of the topic. So what is the advantage you are having? You are increasing the complexity, but what is the advantage? Can you please highlight that?
the advantage in the start of the presentation represent the difference between mixed element and the original finite element method. In the finite element method, we approximate the underlying derivative less than their original part. So it means we have a weak solution, one less than the original part. If we have a solution up to their original part, that will become a classical solution. Here we are getting the solution up to their original part, not less than the original. This is what we achieve. Yes.
Okay, my question is with regards to the condition you use for proving the existence of solution. So why didn't you use last milligram? Did it fail?
Lex milligram can apply on when we are approximate our underlying approximation space is single. Here we have more than one approximation space. That's why.
No, Lex milligram, there is also boundary recursive and boundary linear function. That is the extra conditions.
This
Because
is
we
most
have-
general case you make.
Because we have another weak formulation. We said that that P is equal to something like U. We put, so for that reason we have to need the another conditions for existence and uniqueness of the solutions.
But you didn't show any numerical computation. You're not supposed to, or
Our target is just analysis of.
or just the analysis of that? No computing.
Some
But
of-
you said you used MATLAB, so where was that?
No, doctor.
You used the word MATLAB.
Give us option.
So there's two type of project. Either it's computational or error analysis and so on. So
Oh, I see.
they select, the.
Oh, this lab
analysis
is,
part,
yeah,
yeah.
error analysis.
Yeah.
Error
Our
analysis.
friend had another presentation.
The second
about-
one, they,
I mean, of course, mixed finite element is a well-established theory, and there are many reasons that you can back points, but you use Word for this type, right? You didn't use latex, right? Now, normally, when in the student life, we suggest our student at first semester, you start using latex. Because when edit, you can download, and the best time is to learn student life.
yes.
I am so slow, you see, because I keep postponing and postponing.
Yeah.
And when you get out, you never run back. So this is the best time for you, that because you will be writing, and you see how clumsy is it in
Yes.
this web, like your class type of thing was one day, one type it was product, one this, and it's very, very time consuming by this way. But nowadays, these beavers are there,
Yes,
so
exactly, yeah.
you can just use that one.
Look like
It's in the beginning, it's just matter of using it, but once you start, right, and keep doing it, then you will become expert, and it's very friendly. Nowadays, MATLAB, this latex is very, very friendly, and it used to be very hard. But then, and also that MIC something,
Mid-text.
yeah, you can download that one. That's Compiler is also very good, you know. So hope that next time your presentation is with latex, you know, just make a resolution. Right?
Inshallah, we will submit our budget report.
Whenever time permits, you know, I know students are under always a very high constraint, but believe me, this is the time.
Yeah.
Because I initially postponed, and I am so slow, still after doing that, and my students are so fast, you know, I mean, they will type just like that. It is just comes with the, and it's so handy these days, and it looks much better than MS Word. So I mean, it's just a suggestion, I mean,
Thank you.
you know, I mean, there's nothing wrong with this either. But mathematicians, you know, mostly when you are with mathematics, you go with the latex, and that will be, you know.
Okay, I have a question regarding the discrete spaces you show us. I mean, piecewise quadratic, is it right?
Yes.
Piecewise linear.
Yes.
Okay, and do you think this satisfies the discrete Ipso condition?
Yes.
How do you prove that it is, satisfying the discrete variant of the Ipso condition? Any idea?
I think the calculation similar to this one. Here we are using equilibrium norms, right? But we don't have this condition in V, the VH, discrete space.
Okay.
For discrete space, and one more thing here. And we use this coercivity and start with this coercivity, then we reach to where we have to use the equivalent condition because we are using quadratic. BH is quadratic here. Piecewise quadratic.
Okay.
When we apply H1 norm, so we have a grade of phi. Grade of phi that will vanish. That will reach to a constant.
Okay.
So it's mean our L2 norm will be greater than the H1 norm by applying this one.
Okay. Okay, can you show me that, that the linear system, which is the A and B transpose and B, you mentioned in the last line it is symmetric positive definite A. Okay. Yeah, what about the whole matrix? Is it symmetric positive definite? A, B transpose B 0?
We have to solve this linear system
Yes.
by applying a property weight method. Simply, if we apply a matrix method, this will be it should be invertible here.
Okay.
So it should be invertible. If it is invertible, then it should be symmetric positive.
It is invertible, but it is symmetric positive.
Symmetric positive.
It is application.
Are you sure? And what about if it is not symmetric positive, then it's not invertible?
Invertible depends
So
on
is it a-
non-singularness.
Is it a necessary condition or a sufficient
No, I
condition?
think that's not necessary condition. I think no need to make it symmetric positive.
We
Yeah.
can check it by X transpose Ax is greater than 0.
Okay.
Positive definite for that case.
Yeah.
But no need to, I think. Yes, this is symmetric positive, this should be symmetric positive. Or that one.
What do you mean by positive definite?
Positive definite, all
Something related to eigenvalues?
yes, it is related to eigenvalues. Eigenvalues are positive. Yes.
Positive.
Positive. All eigenvalues are positive.
So it is.
So eigenvalue just depend on the diagonal.
If it is triangular,
What about if it is indefinite, not positive definite? It is indefinite. need to support him about this condition. If it is indefinite, you have the value which is 0.
Yes.
So it is not invertible.
So you mean, I think it is zero.
So this condition is important.
Because we are just focusing on the analytical part. Not the existence of the solution.
Okay.
Can I ask?
Yeah, sure.
You take in the discrete spaces quadratic and linear. Is of course, in the computation it will be a little bit complex. Or is there a problem if you choose 1 degree less? By piecewise linear and piecewise constant, or is there a problem?
Because for the distance of the solution, distance of the solution of the original one, then we are considering this space where we have this inner product goes to 0.
You take the value piecewise quadratic,
Constant.
and you know in the computation you will take integral, and if you integrate linear, it is more difficult than if you integrate constant.
Yes. There are many choices. We just apply one of the choices here. There are many choices. So we are good enough to take this.
Okay, thank you very much.
Thank you.